In this video, I want to show you two simple fake lighting methods that are often used to optimize certain projects. The first one is called, well, I guess we can call it fake vertex lighting, I suppose. And basically what it does, sometimes you play games or you're making a game. In our case, you have scenarios, maybe you don't have a high exposure range, or maybe it's difficult to see various characters in different environments. So you end up in a situation where you might want to have some stylized lighting, or maybe you want to be a bit more creative, so to speak. Now, obviously, this is not super advanced in any way, because I wanted to keep it simple. But obviously, if you want to learn more about it, all you got to do is leave a comment, subscribe, and I might reveal some more stuff. So basically what this does, it helps see the character a bit more where you otherwise would not be able to see them. And what it does, it connects some fake lighting onto your character. Obviously you need to adjust it even more by not having it this dark and so on. But I'll show one method of doing it the simple way, and I'll show another method which costs a bit more, but still serves the purpose. So basically what's happening here is we are using a light position, which is basically 3 vector. We're using object position, we're subtracting it, then we're normalizing it, connecting it to dot, then using the VertexNormalWS, and then just using base color. So basically what does that mean? Well, good question. Well, I'll try and explain it to you so you actually understand. So the light position is a 3 vector, which is basically I hold down 3 and I get the 3 vector, which you probably already use for baking colors, right? So the way the 3 vector works in this case is that obviously this node, it represents a constant vector. It's often used for defining position or direction, such as the position of the light source in this case. So the simple math is that the 3 vector, it's defined by x and y and z coordinates. Okay, so you have the x, you have the y, and you have the z coordinates. Okay, they represent position or direction in space, right? So the light position, for example, could be 50, 100, and 200. Now, in our case, it's quite a bit now, but let's just change it to make this easier for you to understand. And you can see that the fake light is being adjusted accordingly, and obviously it's going to adjust to the character at the back there as well. Okay, obviously that's the wrong direction, because that's not necessarily the wrong direction, because the shadow is already put to us facing this way, so you can still see it works. Okay, so just think of so this basically means that the light is located at x50, y100, and z200. So just to visualize this, just think of a lamp in a room, and the coordinates are the x, y, z, and then we specify where the lamp in the place the room is, and then you trying to understand where the light is coming from. So obviously in this case it's the sunlight, the fake sunlight, and we're saying it's coming from this direction. Okay, now they work together by combining it with object position. So the thing with the object position is that, how should I explain it? So the object position, the purpose of the object position is this node provides the absolute position of an object in the world space. It's like the GPS coordination in the 3D scene, so to speak. So the simple math is similar. You have an x and y and z. Okay, so in this case we would want to change this, obviously, because we want different numbers. So the numbers might be 10, 20, and 30, meaning 10 in x, 20 in y, and 30 in z in this case. So just imagine placing a pin on the map, and the coordinates, which is latitude and longitude, tells you exactly where the pin is. So the opposite positioner tells us where the object is in 3D space, basically. So whenever I move, whenever I decide to move the character, you know, it doesn't ruin our fake lighting, right? So that's basically what is happening there. Now for the subtract, so if point A, so we're gonna call it PA. Point A is 2, 3, and 5, so XYZ coordinates, and point B has 7, 8, and 10, so still XYZ. We're using the subtract, gonna call it sub, and we're basically saying 7 minus 2, and 8 minus 3, and 10 minus 5, which equals 5, 5, 5. Okay, so this tells us that moving from point A to point B, it involves moving 5 units in each direction. So just imagine that you're standing at point A and we want to reach point B, and the subtract node tells you the path you need to take. It's like an arrow basically pointing around. Okay, and then we put the normalize, basically what we use the normalize for, arguably. And then we have normalize. Normalize, it converts a vector into a unit vector, meaning it only keeps the direction and makes its length 1, right? So if by this calculation, if this goes all the way to 1000 length, we are just saying we want to normalize it down to 1. Okay. So example, if the vector is so if the vector calculation is 3, 4, 0, and the length is 5, the normalize is going to calculate 3 by 5, 4 by 5, and 0 by 5. Which basically makes it 0.6 and 0.8 and 0. So it stays within 0 and 1. And what does the dot do? The dot product basically calculates how similar two vectors are in terms of the direction. In simpler terms, it measures how much one vector points in the same direction as the other. So what we're trying to figure out here is we have two vectors. So we have vector A, and we have vector B. Okay, and the dot product is basically calculating again x, y, and z's. So if vector A is 1, 2, 3 in all of these coordinates that we've been using, and vector B is 4, 5, 6 in all these coordinates, the dot product is basically saying 1 multiply by 4, and it's doing the same, 2 multiply by 5, and 3 multiply by 6. And when you do all of that, it's 4 plus 10 plus 18 equals 32. So it knows that the dot product, the calculation is 32, which indicates the similarity in direction between two vectors. Okay. Now the dot product, let's see if I can explain it. It's basically it's comparing two directions. Okay, so the purpose is to measure two vectors point in the same direction. So it's a way to determine the angle between two vectors, which can be useful in our case for lighting. So the way I understand it is there is a vector, we call it vector A, and there is a vector B. Okay, and in vector A, let's say it's 1, there's 2, there is 3, and on vector B there is 4, and there is 5, and then there is 6. And basically it's multiplying 1 by 4, multiplying 2 by 5, multiplying 3 by 6, and then plussing it together. Okay, this would be 32. Okay, so dot product is 32. Okay, now I know you're going, what does that even mean? Well, but you have to you're gonna have to bear with me a little bit there as I try and give you another example, depending on how your brain works. So that's the calculation for a dot product. Now, if you're looking for perpendicular vector, so you're looking for two vectors that are perpendicular, so 90-degree apart, the dot product would be 0, right? So you have vector A. You have vector A, and you have vector B again, okay? And in this math, the vector A is 1, 0, and 0, and vector B is 0, 1, 0. This is now doing like 1 multiplied by 0 plus 0 multiplied by 1 plus, and 0 multiplied by 0. Mathematically that's 0, right? So there is they're basically 90-degree apart, so this can also go in negative, I believe. Okay, so that's how that works. Now if you want to calculate the way it works when it's calculating the what is called the parallel vectors, so that's when two vectors are pointing the same direction, which is what we're looking for. Or we're looking for all of this. So I'm showing you the math for each scenario that's happening here. And their dot product is the product of their magnitude. So again, similar if it's pointing the same direction. 1, 2, 3. And we have vector B. You have 2, 4, 6, which is a scale version of A. And here again, you multiply, plus you multiply, you plus and you multiply. And this is 28. So now, bear with me as I try and explain this. Just visualize, all right? We're going to visualize two arrows in the 3D space. Okay, we're looking for two arrows in 3D space. Their dot product tells you how much one arrow points in the same direction as the other. So all the math we just did essentially is doing this. This arrow is pointing this way, and the character is pointing, I don't know, this way. Okay, so if the arrow points in the same direction, the dot product is large. If they're perpendicular, the dot product is 0. If they point in opposite direction, then it's negative. Okay, so in theory, this is, you know, I guess it's closer to 0, somewhere around that, to make my life easy and your easy. And if they're pointing the same direction, so now let's imagine this one is pointing exactly the same direction. Now we have a large dot product, so it's close to the map. So in the context of what we're doing, the light direction vector, it represents the direction of the light source to the surface, which is the vector A in this case. And you have the surface normal vector, which is the vector B we were doing. Okay, these represent the direction of the perpendicular to the surface. Vector A represents the direction of the light source to the surface, so A against the B. And the dot product of these two vectors tells us how much the light hits the surface. So if the dot product is close to 1, the surface is fully lit. If it is 0, the surface is in shadow, right? So if these two are close, it is now 1. If these two are not, it's in 0, meaning this side is in 0, mind you. Okay, so just think of a shining flashlight on the wall. That dot product tells you how directly the light hits the wall. If the light shines straight on, it's bright, which means it's a high dot product. If it shines at an angle, the brightness will decrease, so this is a lower dot product. Now, hopefully that makes sense. If not, well, when I can explain it better, I will explain it better. Now, you have the VertexNormalWS, right? So as I was explaining with the dot, you have the vector A and vector B. So the vector A number is coming from here, whatever the numbers I was randomly telling you. Now we are getting information from this one, which goes into vector B, and that's what's being compared. So the way the vertex normal node, it's very important for the lighting effect to work here. So the purpose of this vertex normal in world space, it provides the normal vector at each vertex of a 3D model in the world space coordinates. So basically a normal vector is a perpendicular line to the surface at the vertex, and it's indicating the direction the surface is facing, because we want to know where the character is looking, or what the surface is looking at, this case the material, towards against the light direction, the fake light direction we have here. Okay, so example, simple math is usually represented in X, Y, Z. These values indicate the direction the surface is pointing in 3D space. So for example, flat surface, imagine a perfectly flat ground. The normal vector for this ground would be 0, 1, 0, and this one is pointing straight up, kind of up, but it's supposed to be straight up. Okay, in example 2, you have a hillside, like a slope surface. The normal vector would be 0, 0.5, 0, 0.5, and 0. This indicates that the surface is tilted with a 55-degree slope. Okay, so what does that mean? Obviously, it's not straight anymore. It's pointing this way, kind of. So visualize it. Think of this. Think of the normal vector as an arrow. So this is the arrow perpendicular to the surface. For the flat floor, the arrow points straight up. For the slope tilt, the arrow is obviously tilting to match the slope. So they are matching the surface of the slope. So when the light hits the surface, so basically when the light hits the surface on the flat floor, just imagine that the arrow points straight up, and for the slope tilt is matching it. Okay, so for the direction of the normal vector, it affects how the light interacts with the surface. If the light hits straight on, the surface is fully lit. If the light hits an angle, the surface is partially lit. So we're trying to figure out between these two, these are our vectors, vector A and B. Are you looking at each other, or are you in an angle? Are you in a sloped angle, or are we looking at straight at the other? So just imagine that you are imagine you're holding a flashlight, shining it on a different surface again. If you shine it straight onto the wall, the light is bright. If you shine at the angle, the light spreads out and is less intense. So the vertex normal world space node helps simulate this effect by providing the direction each surface is facing, which affects how the light interacts with it. So when this goes into the dot, we kind of calculate whether or not you're facing each other or not. So if I do this, it's calculating, are you facing the surface or are you not facing the surface? If you're facing the surface, you're going to be bright. If you're not facing the surface and it's not matching, you're going to go dark. Okay, so that's basically what's happening there. And for some reason this went weird. Okay, and that's that. Okay, so you can actually get the information from the skylight, sky atmosphere light direction. So we're going to go for sky atmosphere light direction, and we're going to use the vertex normal that we already mentioned, because we need to know the direction and everything. Then we're going to calculate it all together with the dot again, so we can compare between everything that's going on. I'm going to leave that there, and then I'm going to do a duplicate of this, and I'm going to put that here, and I'm going to do gonna have the skylight calculation too, and that's, I normally use the skylight environment map sample, and I'm going to add a reference, otherwise you get the reflection of the sky, but we can show you that. Okay, now these two needs to be combined together. But first I need to clamp, so to speak, the dot product, and there is a node that can do that as well, which is cheaper apparently than clamp. I'm going to use saturate. I think that's what it does, if I remember correctly. Then I'm going to add it together here. So we want to combine what we already have. I'm going to add a multiply. And the reason I'm adding multiply, instead of putting it directly to the add, actually I'll show you. So we're just going to do that. We're going to do that. Okay. And now if we have a look, let's just make sure it's all actually working first. And okay, and let's go in the front. So you can see it got pretty bright. Okay, now if I turn this to 1 and I do apply, all right, so you can see it's kind of working, and it's a bit more brighter than this one, obviously. Okay, now the reason I want to use a multiply is just to give a little bit more control over certain things. So I'm going to connect this in here, and I'm going to connect the skylight environment into the multiply, and I'm going to hold down 1 to have a parameter, and I'm going to convert it to a parameter and just like call it bounce light. And then I'm going to do 1, and you can see what happens there. If I go 1.2 and I apply it like this, okay, so I could go all the way down to, so let's say if I just did 1, you can see what happens, right? So you can have smaller values, so 0.2, 0.1, right, to create the shape that you need out of it. Okay, and essentially you could keep making that more advanced. You could, I believe you could multiply and add a bounce light for the directional light too, if you wanted to, and you can keep improving it and improving it as you need. So what this does, you know, as you change the direction, it's going to change the direction of this, because it's still a kind of fake, but what's happening is you don't have to manually do it anymore, right? And then you can do what you need to do to tweak it. Okay, so hopefully that's useful. I thought that was kind of useful when I was working on gonna work on a project, and I never completed this, but this was the beginning of it, and I thought it might be useful for someone else. So hopefully it's fun, it's useful. So just leave a comment, leave a like, and let me know what you think, and see you around. Bye bye.